So, welcome to lecture number 24 of our course on fundamentals of transport processes. We were just about finishing up on our discussion of viscous flows in the low Reynolds number limit. These are low Reynolds number viscous flows, and as I told you, the governing equations are the Stokes equations. The divergence of velocity is equal to 0, mass conservation, incompressible fluid, and the momentum conservation equation. Okay, so, these were the governing equations, and we had solved it in various situations, both for external flows outside an object. I showed you how we can reduce this Stokes equations to two Laplace equations for the general part of the velocity profile and for the pressure. Okay, so, and the total velocity is equal to the general part plus 1 by 2 mu p times the position vector in the coordinate system. And we looked at various interpretations of this. The solution becomes particularly easy when you are solving around a spherical object, because there are no other vectors in the system. Therefore, the solution has to be linear in the velocity of the object and in one of the spherical harmonic solutions. We looked at how to derive spherical harmonic solutions, vector tensor solutions, just by taking the gradients of the fundamental solution. The fundamental solution is just 1 over r in 2 dimensions. You can try to work it out yourself. You will find that in 2 dimensions the fundamental solution is log of r. In 3 dimension the fundamental solution is 1 over r, and by taking repeated gradients you can get all vector, tensor, and any higher order tensor solution for the equations. And just from linearity and reversibility, we know that the solution has to be linear in one of those scalar, vector, tensor solutions, and linear in the velocity of the object itself. And on this basis, one can construct solutions which satisfy boundary conditions and use these to determine the force on an object that is moving in a viscous flow. A force on a sphere was of course given by Stokes' law. In that case, there was a net force on the particle, and the velocity decayed as 1 over r far away. So, when you have a net source, the decay is proportional to 1 over r. We also consider 2 other situations where either we had a rotational flow far away or an extensional flow far away. In those 2 cases, there was no net force. However, there was a net torque or a net force moment. The velocity field due to these decayed as 1 over r square. And we saw how to construct the solutions due to these force moments, both the symmetric and the antisymmetric force moments, resulting in respectively a net symmetric force moment is due to an extensional flow far away, a symmetric traceless rate of deformation tensor. The antisymmetric force moment is due to the rotational flow far away. And in both those cases, the solution decays as 1 over r square. These decays are general in the sense that they are applicable to any form of the any shape of object. There will be higher order terms, of course, which we have neglected, but the slowest decaying terms, if there is a net force on the object, has to go as 1 over r. If there is no net force, it has to go as 1 over r square if there is a net force moment, and so on. We also saw how to reduce the Stokes equations in 2 dimensions to a Bi-Harmonic equation. So, in that case, if you have a 2-dimensional flow in the x y Cartesian coordinate system, u x, you can write it as in terms of the stream function and the resultant mass conservation equation is trivially satisfied when the velocities are expressed in terms of the stream function. The momentum conservation equation, when I express the velocity in terms of the stream function, gives me the Bi-Harmonic expansion del square psi is equal to 0. Okay. Or alternatively, it is called the Bi-Harmonic equation. The fourth order derivative acting on psi is equal to 0. And we also saw how to solve this equation for the particular case for the flow around a corner. And finally, we looked at the flow in between surfaces that are nearly in contact with each other. The specific problem that we solved was the velocity of a sphere settling in a fluid for the case where the radius of the sphere was much larger than the distance between the two surfaces. And in this case, we used scaling principles because this is a nearly unidirectional flow. The distance between the surfaces is small compared to the lateral extent, and therefore, the flow is nearly unidirectional. At any point, if you do the scaling analysis, you will find that the velocity profile is close to a parabolic profile, and using that one can find out what is the pressure difference between the center of this gap and the ambient pressure, and that difference basically drives the flow. From that you find out what is the force acting on this object, and it turns out to be 6 pi mu r u by epsilon. So, the force increases proportional to 1 over epsilon as the distance between the two surfaces becomes smaller and smaller. So, this in summary is what we have done so far in Stokes' flow. There is one further little bit that we need to do, and that is when we solved the Stokes' flow equations, we assumed that the convective effects could be neglected everywhere in the fluid. That is, diffusion is dominant. Diffusion is dominant means that the momentum diffuses instantaneously throughout the entire domain. Okay. However, the domain is infinite in extent. If you take, for example, the flow around a spherical object, can the momentum really diffuse everywhere instantaneously when the domain itself is infinite in extent? Is there going to be some distance beyond which inertial effects will become important even though the Reynolds number is very small? So, let us look at that question. Can I really consider that diffusion is instantaneous throughout the domain even when the domain is very large? In other words, if I have a sphere in a very large volume of fluid and I push the sphere some distance or apply a force on the sphere, there is going to be a disturbance to the velocity field. Stokes' equations are quasi-steady. That means that the disturbance to the velocity field depends only upon the velocity, instantaneous velocity of the sphere. However, the information cannot really travel instantaneously. Right? If I change the velocity of the sphere, I cannot expect that even very, very far away there should be a velocity disturbance which happens instantaneously coinciding with the velocity disturbance on the sphere. Okay. So, let us look at that question. What are the inertial corrections? To Stokes' flow. So far what we have been doing is to consider a sphere moving with a velocity u in some direction in a fluid where the velocity is equal to 0 as r goes to infinity, okay, where I fixed my origin at the center of the sphere. Okay. So, that is the problem that we have been solving so far. What I prefer to do for discussing inertial corrections, because when there are inertial corrections, the quasi-steady approximation no longer is valid. Therefore, I cannot just sit on the surface of the sphere and assume that nothing changes outside. We will come back to that when we discuss potential flow in the next lecture, but for the present rather than having the sphere moving with a velocity u and the fluid stationary far away, I prefer to discuss a system where the sphere, the velocity of the sphere is equal to 0 on the surface, and the fluid is coming in with a velocity minus u far away. R goes to infinity. Okay. U is equal to minus u as R goes to infinity. Minus u far away from the sphere at all points. Okay. So, there is a uniform velocity far away from the sphere. The sphere of course is stationary, therefore, one would expect there is a velocity disturbance in the vicinity of the sphere. Okay. The sphere is stationary, and in order to keep it stationary you have to exert a force on the sphere. Because there is a net force exerted on the fluid, there will be a velocity disturbance due to the sphere. Okay. So, therefore, the velocity field I can write it as u vector is equal to minus u velocity far away plus a disturbance due to the presence of the sphere u prime. U prime itself is a function of x, u vector is a function of x, capital U is a constant. It is the velocity with which the fluid is moving far away from the sphere. So, now this configuration is exactly equivalent to the sphere moving in the fluid stationary, but it is easier to analyze this particular problem. Because this is just a Galilean transform, it involves just translating the entire equipment with the velocity minus u. The forces that are exerted should be identical, and the velocity u prime that I have here, the velocity u prime that I have here, the velocity disturbance should be identical to the velocity u that I have in this configuration, because in this in the top configuration the fluid velocity goes to 0 far away, therefore, the velocity disturbance is just u. In the bottom configuration the fluid velocity is minus u far away, and therefore, the velocity disturbance is u prime, and the two have to be equal. So, let us go back to the Stokes equations. Now, what happens when the Reynolds number is small, but not 0? My equations become del dot u is equal to 0 and Reynolds number times, in this bottom configuration it is a steady configuration. So, the time derivative of the velocity disturbance has to be equal to 0. Note that capital U itself is independent of position and time. Small u prime is a function of position, but since the configuration is steady, it is independent of time. So, I will get R e into u dot grad u is equal to minus grad p plus mu del square u. And I substitute for u from this expression in terms of minus u plus u prime. Okay. Note that the gradients of capital U are 0. Okay. Therefore, any term that contains the gradient of capital U has to be 0. Into grad u prime Okay, so, that is the equation when expressed in terms of the velocity disturbance. Note that this convective term has both the steady velocity far away as well as the velocity disturbance. Now, let us estimate the various terms in this equation. As I said, the velocity u prime is identical to the velocity that you have in the fluid for the case where the sphere is moving and the fluid is stationary. So, therefore, since there is a net force exerted by the sphere on the fluid, one would expect that the velocity u prime is proportional to 1 over r as r goes to infinity. Net force of the sphere on the fluid implies that the velocity has to be proportional to 1 over r. Okay. because there is a net source of momentum. Now, if you take, I should get rid of the mu here. Let me write it in terms of dimensional equations. Okay. Okay. U prime is proportional to 1 over r as r goes to infinity. What about the gradients of u prime? Okay. Every time you take a gradient, take the derivative of 1 over r, it goes as the next higher power of r, okay, 1 over the next higher power of r. Okay. That means that grad u prime should be proportional to 1 over r square, and del square u prime should be proportional to 1 over r cubed. So, now I have the governing equation. Okay. Now, I will define my scaled coordinates, okay, as r star is equal to r by capital R, okay, and u prime star is equal to u prime by capital U, where u is the velocity of the with which the fluid is coming in far away from the sphere. Okay. And you can easily verify once you do this scaling that the net result that you will get is R e into minus u star plus u prime star dot is equal to minus where the Reynolds number R e is equal to rho u r by mu. Okay, so, there is a Reynolds number, and of course, I have defined the scaled u star vector is equal to u vector divided by the scalar magnitude of its velocity u, and the divergence del star is equal to r inverse, okay, times the gradient. Okay. Because capital R is the only length scale in the problem, which is the radius of the sphere. Okay. So, that is how I have defined the gradient, the scaled gradient. Okay. So, in terms of scaled variables, u prime vector has to be proportional to 1 over r. Okay. What that means is that u prime star has to be proportional to r by r, okay, because u prime star is scaled by capital U, okay, and therefore, it has to be proportional to capital R by r is dimensionless. Okay. If I take one gradient, okay, if I take one gradient is proportional to r by r the whole square, and two gradients proportional to r by r the whole cubed. Okay. So, now let us just put in these dependencies. Okay. Let us just put in these dependencies in the equation. Okay. So, I get the first term R e into minus u star plus u prime star dot okay. So, that is the equation, and I will put in the dependencies here. Okay. This u prime star is of course independent of the radius r, because it is just a constant velocity. Okay. So, this is order 1, okay, it is independent of the radius r. U prime star is proportional to capital R over small r. Okay. U prime star is proportional to capital R over small r. Okay. So, this is over small r, okay, and I have the gradient here, which is r by r the whole square. Okay. Then there is the gradient of the pressure plus the second derivative of the disturbance to the velocity field, and this goes as r by r the whole cubed. Okay. the assumption in the Stokes flow equations is that the Reynolds number is small, okay, that the Reynolds number is small. Okay. However, you can see that the largest term on the left hand side, is proportional to the Reynolds number times u prime star multiplied by the gradient of u star. Okay. So, it is Reynolds number times r by r the whole square. Okay. The largest term on the right hand side, at least as far as the velocity gradients are concerned, goes as r by r the whole cubed. Okay. So, clearly even when the Reynolds number is small, the term on the left hand side becomes comparable to the term on the right hand side. Okay. Inertial terms become important. Okay. For r by r is proportional to Re inverse. Okay. So, when r by r, small r by capital R is proportional to Re inverse, you can see that this term on the left hand side is of the same magnitude as the term on the right hand side. Re inverse, inverse of the Reynolds number. So, there is going to come some radius, some radial distance from the object at which the inertial and the viscous terms are going to become comparable to each other. That radial distance is proportional to inverse of the Reynolds number. So, that distance becomes larger and larger as the Reynolds number becomes smaller and smaller. Okay. So, this simple calculation states that even when the Reynolds number is very small, there has to be some large radius at which inertial terms have to become comparable to viscous terms. Okay. R by r is proportional to Re inverse. If I write that in terms of the Reynolds number, I get r by r is proportional to mu by rho u r, okay, or r is proportional to mu by rho u. Okay. So, this distance at which the inertial terms become of the same magnitude as the viscous terms, okay, does not depend upon the radius of the object itself. It depends only upon the velocity u as well as the density and the viscosity of the fluid. And once you go to that sufficiently large distance, it is no longer sufficient to solve only the viscous terms of the conservation equation, because the inertial terms of the conservation equation have become comparable to the viscous terms. So, clearly, if I have to solve for this particular problem, if I have to solve the complete equations, the equation becomes Re into minus u plus u prime dot grad u prime is equal to minus grad p plus mu, should have no. Okay. So, now I have to solve this complete equation if I am sufficiently far away. However, one can make a simplification, okay, because this minus u, this is always going to be order u. Okay. This thing is always going to be order u. Okay. Whereas, this term here goes as 1 over r. Okay. This term here goes as 1 over r. Okay. If you are sufficiently near the object, the Reynolds number, if the distance for r by r smaller than Re inverse, I can neglect this entire term. I can neglect the entire inertial term on the left for r by Re is much smaller than Re inverse. Okay. On the other hand, for r by r larger than Re inverse, I cannot neglect this inertial term, because the inertial term is comparable or larger than the viscous term in that case. However, within the inertial term, I have two velocities minus capital U plus u prime, and when r becomes large, u prime goes as 1 over r, whereas capital U itself remains independent of distance, because it is a constant, it is the velocity of the fluid far away. Therefore, in that case I can neglect u star prime is small compared to u star. Okay. So, I can neglect u star prime in comparison to u star, and I get a simplified equation for the velocity disturbance. Okay. You get a simplified equation for the velocity disturbance. Okay. Note that I have neglected one term, and that is the disturbance to the velocity field u prime, okay, in the inertial term. Okay. The rationale is that when r is small, entire inertial term is small anyway, so I can neglect it. When r is large, u star prime becomes small compared to capital U, and therefore, it can be neglected. So, this is the simplified equation. It is called the Oseen equation. This includes the effect of inertia far away, while neglecting the velocity disturbance far away, because that is small compared to the steady velocity with which the entire fluid is moving. This equation can be solved. The solution procedure is rather complicated. Okay. So, the entire Oseen equation in dimensional form is given by rho u dot grad u prime plus mu del square u prime for the disturbance velocity profile. Okay. This is still a linear equation. Okay. This is still a linear equation. That is because I have neglected the nonlinear term, which goes as u prime dot grad u prime in this equation here. Since I neglected that nonlinear term, I get still a linear equation. However, it is now no longer reversible. The reason is because I have u dot grad u prime. Okay. So, if I were to interchange, if I were to reverse the direction of the velocity everywhere, on the right hand side the velocity and the term on the right hand side is linear in the velocity, and so it reverses, whereas the left hand side term is not. Okay. So, in this case it is no longer a reversible flow. Okay. So, it contains it is now irreversible, that is, if you interchange the direction of the velocity within the fluid, I am sorry, if you interchange the velocity at the boundaries, the velocity everywhere within the fluid no longer reverses. Okay. However, it can be solved. The solution is a little complicated mathematically, so I will just give you briefly how it is done. In this case, the configuration is axisymmetric, okay, because I have symmetry around the direction of motion of the sphere. The sphere is moving with the velocity u. Around that axis parallel to u, the configuration is axisymmetric. So, one can reduce it. So, there is no dependence of the angle, the meridional angle going around this velocity direction through the center of the sphere. Therefore, one can solve this in an axisymmetric coordinate system, in which the coordinates are just the distance r and the angle theta. Okay. There is no dependence on the angle around the there is no dependence of the angle meridional angle phi around the axis parallel to the velocity vector. Okay. So, in that case it is possible to find a stream function formulation. Okay. If I write u r is equal to 1 by r square sin theta partial psi by partial theta, and u theta is equal to minus 1 by r sin theta partial psi by partial r. This will identically satisfy the axisymmetric mass conservation equation, that is 1 by r square d by dr of r square u r So, this equation is identically satisfied with this formulation of u r and u theta in terms of the stream function. These are inserted into the conservation equations as usual, and you will end up with the Bi-Harmonic Equation, which has to be solved analytically. The solution is not easy to derive, but it is quite easy to verify. Okay. It turns out the solution is of the form psi is equal to u r square into minus 1 by 4 r by r sin square theta plus 3 1 minus cos theta 1 minus e power minus 1 by 8 r e into 1 plus cos theta r by r divided by 2 r e. So, that is the final solution that you get, where r e is equal to rho u r by mu. You can very easily verify that very near the surface of the sphere itself, it will give back the solution that we had earlier. In that case, you are taking the limit where r by r is very much smaller than r e inverse. Okay. Note that in the exponential, I have an r by r here and r e here. Okay. If r by r is much smaller than r e inverse, then the term in the exponential will turn out to be independent of r e, okay, because when I expand this out in Taylor series expansion, I will get a term that is independent of r e. Okay. And the stream function for that case will just turn out to be equal to u r square sin square theta into this turns out to be the identical solution that we get for the flow around a sphere. Okay. However, this additional term here results in a correction to the drag law, okay, to the drag force in the sphere. There is a correction to the drag force in the sphere due to this additional term. Okay. And this correction has been calculated exactly. Okay. Is equal to 6 by mu r u I 1 plus 3 by 8 times r e. And this is called the Oseen correction. The Oseen correction to the drag force on a sphere due to inertial terms, due to the inertial contribution far away. So, this is the leading order correction in the limit of small Reynolds number. So, the summary of the effect of inertia at low Reynolds number is that inertia can be neglected if you are sufficiently near the surface of the sphere, if small r by capital R is less than r e inverse in the limit as r e goes to 0. Once you go beyond that, inertial terms do become comparable to the viscous terms, and you can no longer neglect the inertial terms of the conservation equation. Okay. However, even though you cannot neglect the inertial terms, you can still reduce it to a linear equation, the Oseen equation for the velocity profile. This is still linear in the velocity u prime, but it is no longer reversible because it contains capital U dot grad of u prime. So, it is no longer reversible, but it is still linear. That can be solved, and because of these inertial effects, you get a correction to the drag force on the sphere, which goes as 1 plus 3 by 8 times r e. So, that is a summary of the effect of inertia at low Reynolds numbers. So, this completes our discussion of low Reynolds number flows. Next, we will go on to flows in the limit of high Reynolds numbers. Okay. High Reynolds number, what we will call as potential flows. Okay. High Reynolds number potential flow. The equations once again, the Navier-Stokes equations, del dot u is equal to 0 and rho into partial u by partial t plus u dot grad u is equal to minus grad p plus mu del square u. Okay. Plus any body force that is exerted. Okay. So, that is the mass and momentum conservation equations. In the case of potential flows, the assumption is that the viscous effects are small compared to inertial effects, because we are in the limit of high Reynolds numbers. Therefore, the viscous effects can be neglected in comparison to inertial effects. That is, I can neglect this term in the conservation equation in comparison to the inertial terms. That is one approximation, inviscid. That is, the flow is inviscid, that is, the viscous term is negligible, and therefore, I can neglect it in the momentum conservation equation. The second assumption for potential flow is that the flow is what is called irrotational. The flow is irrotational. That is, there is no rotation at any point within the flow. The rotation is related to the vorticity, okay, is equal to del cross u. That is equal to 0 at each point within the flow. Okay. So, that is the second assumption for potential flows, that the vorticity is equal to 0 everywhere in the flow. Therefore, the curl of the velocity is equal to 0 everywhere in the flow. Under these two conditions, the flow is called a potential flow. Okay. Clearly, the viscosity can be neglected when the Reynolds number is high. In addition, you require that there is no rotation locally anywhere within the flow. So, that is, the inviscid irrotational flows are called potential flows. Reason is because, as we know, when the curl of the velocity is equal to 0, curl of any vector is equal to 0, the vector can be expressed as the gradient of a scalar. Okay. Because if the curl of the vector is equal to 0, vector can be expressed as grad phi, okay, such that, because we know that the curl of the gradient of any function is equal to 0. Okay. This phi is what is called the velocity potential. Okay. It is called the and the velocity is equal to the gradient of the potential. So, therefore, I have reduced the velocity from two components can be expressed in terms of just one scalar component, or three components can be expressed in terms of just one scalar component. So, once you express the velocity as the gradient of the potential, then you can see that this reduces to del dot is equal to 0. Okay. Or the Laplacian of this potential has to be equal to 0. Okay. So, that is the equation of motion for the velocity potential. So, that is the equation for the potential. The momentum equation, of course, gives me the pressure, okay, in terms of the velocity fields. That once again can be simplified in this case using the fact that the flow is irrotational. Okay. It can be simplified using the fact that the flow is irrotational. So, let us see how to simplify that. We will go back to our indicial notations, because that is more convenient in this case, and I neglect the viscous term in the conservation equation. The conservation equation is partial ui by partial t plus uj plus the body force. I have neglected the viscous term. And we will try to find a simplification for this term here, using the fact that the flow is irrotational, okay, and therefore, it is a potential flow. Simplify this as follows. If you take u cross del cross u, in indicial notations, I can write it as epsilon I j k u j times del cross u, epsilon k L m partial by partial x L of u m. This is equal to epsilon I j k epsilon k L m u j partial by partial x L u m. And we know what is epsilon ijk times epsilon klm. It is a product of two antisymmetric tensors, ends up being a real fourth order tensor, and this can be written as delta IL delta Jm minus delta Im delta JL. And I can write this delta IL times partial by partial XL is Ui. Therefore, this will become Uj partial by partial Xi of Uj minus delta Im. So, I get Uj delta JL gives me partial by partial Xj of Ui. Okay. So, that is U cross del cross U. Okay. And we know that the flow is irrotational. Therefore, del cross U has to be equal to 0 everywhere. Since del cross U is equal to 0 everywhere, U cross del cross U also has to be equal to 0 everywhere, okay, because it is irrotational, and therefore, the curl of the velocity vector is equal to 0 everywhere. That means that U cross del cross U also has to be equal to 0 everywhere. That means that Uj partial Ui by partial Xj has to be equal to Uj partial Uj by partial Xi. Okay. And so, therefore, for this term here, what I have here is U rod grad U, Uj times partial Ui by partial Xj. I can substitute instead the first term over here. Okay. So, this basically tells me that partial Ui by partial Xj is equal to, okay, Uj partial Uj by partial Xi. Okay. You would have expected this, and this basically is telling you that partial Ui by partial Xj is equal to partial Uj by partial Xi. That is, the transpose of the rate of deformation tensor is equal to itself. That is, the rate of deformation tensor is symmetric. That is expected in this case because there is no rotation. Therefore, the antisymmetric part of the rate of deformation tensor is equal to 0. I can also write Uj times partial Uj by partial Xi as partial by partial Xi of half Uj square, because if I differentiate this using chain rule, I will just get Uj times partial Uj by partial Xi. This can be written as gradient of half U square. Note that Uj square is the velocity square, U1 square plus U2 square plus U3 square. So, that we will substitute into the equation for potential flow. Okay. So, let us substitute that in here. For the first time derivative of the velocity, I will substitute partial by partial t of velocity, as I said, can be expressed as the gradient of a potential. So, I will substitute the gradient of the potential here. The second term, I can write it as the gradient of half Uj square. Okay. Is equal to minus partial p by partial Xi plus Fi. In the first term on the left, I can interchange the order of differentiation, because the time and position are independent coordinates. Okay. Therefore, this gives me, okay. In addition, the density is also a constant. The density is a constant everywhere, so it can be taken into the gradient. Okay. So, with this I will get partial by partial Xi of rho times partial phi by partial t plus half rho Uj square is equal to minus partial p by partial Xi plus Fi. We have gradients on everything except the body force. If the body force can also be written as the gradient of a potential, that is, it is a conservative body force, okay, the body force can be written as Fi is equal to minus the gradient of a potential. Okay. For example, in the case of gravitational force, the potential would just be rho g times the height. Therefore, the force would be rho times g acting in the direction of gravity. Okay. So, if I can write this in terms of the body force and body force in terms of the potential, my entire equation becomes partial by partial xi of partial by partial xi of p plus v plus rho partial phi by partial t plus half rho uj square is equal to 0. Now, this is equal to 0 everywhere within the flow, the gradient is equal to 0 everywhere within the flow. So, if the gradient of a function is equal to 0 everywhere within the flow, that means that the function is invariant everywhere within the flow. There is no gradient anywhere, so it does not vary as you move from one location to the other. That means that this function has to be a constant. It is equal to a constant for the flow. This is what is known as the Bernoulli equation. Okay. For gravitational flows, for example, for a flow under gravity, this V is equal to rho g times the height. Okay. So, in that case, the equation would be P plus rho g z plus rho half rho uj square is equal to P naught. Okay, that would be the Bernoulli equation for when that potential is the gravitational potential. Okay. The rho density times the acceleration due to gravity times the height. Okay. So, this contains the potential energy rho g z, the kinetic energy. Half m v square is the kinetic energy, half rho v square is the kinetic energy per unit volume. Pressure is an energy per unit volume. Okay. And you have this additional term here, partial phi by partial t, okay, the rate of change of potential. That is the acceleration term. If the flow were steady, then this acceleration term would be equal to 0. However, in general, this acceleration term is not equal to 0. It has to be included in the potential equation. Only in the specific case where the flow is steady, this acceleration term is equal to 0. So, these are the potential flow equations. The gradient of the potential is equal to 0 and the Bernoulli equation P plus half plus any potential that is there is equal to P naught. Okay. Note that we have completely neglected the viscous terms in the conservation equation. That means that the stress tensor is just equal to minus the pressure times the identity tensor. Okay. So, the stress tensor for potential flow is equal to minus P delta Ij. Okay, so, that is the stress tensor. In addition, we have neglected the viscous term in the conservation equation. The viscous term contained the highest derivative, the second derivative of the velocity with respect to position. When we neglected that viscous term, we can no longer apply all the boundary conditions that were there in the original problem. As I said, originally for the Navier-Stokes equations, it is a second order spatial differential equation in the velocities. Therefore, you have two velocity boundary conditions at each surface, no slip condition or 0 stress condition or some constant stress condition. When we neglected the viscous terms, we neglected this highest derivative, and therefore, we can no longer apply all the boundary conditions that were there in the original problem. We neglected the viscous stresses. because we neglected the viscous shear stress, there is no momentum diffusion from the surface. When there is no momentum diffusion from the surface, one cannot apply a 0 tangential velocity boundary condition at the surface, or a 0 shear stress condition, or a constant shear stress condition, because there is no mechanism for transporting momentum along the flow direction. The mechanism for transporting momentum perpendicular to the flow direction, I am sorry, no mechanism for transporting momentum perpendicular to the flow direction, because we have neglected the viscous stresses, which ultimately result in the velocity field coming to 0 at a surface, the momentum diffusion, okay, which results in the no slip condition at the surface. Therefore, we cannot satisfy the tangential velocity boundary conditions anymore. The only boundary condition that we can satisfy is the normal velocity boundary condition, that is that u dot n is equal to capital U dot n. That is, the velocity of the fluid along the normal direction to the surface is equal to the velocity of the surface itself. In other words, both the surface and the fluid have to move with equal velocity at the surface. As far as the tangential velocity boundary condition is concerned, since we neglected viscous stresses, there will be a velocity slip at the surface in the case of potential flows. The tangential velocity in a potential flow will not decrease to 0 at the surface. The reason is because we do not have the mechanism for reducing the velocity, the diffusion of momentum due to shear stresses. Similarly, we cannot impose the tangential stress boundary condition, because the potential flow has 0 tangential stress. We have neglected the viscous terms completely. So, we can only impose the normal stress boundary condition. The normal stress in the case of potential flow is just equal to minus of the pressure, if it is defined with respect to the outward unit normal. So, therefore, these potential flow equations have to be solved with normal velocity and normal stress conditions. So, first we solve this, I am sorry, please correct that should be del square of phi is equal to 0. The divergence of the velocity is equal to 0, or the Laplacian of the potential is equal to 0. So, we solve del square phi is equal to 0 with the normal velocity boundary conditions at the surface in order to obtain a solution for the potential and therefore, for the velocity. That solution for the velocity can be inserted into the Bernoulli equation to find out what is the pressure acting at the surface. So, this is the way that you would solve in case there were velocity conditions specified at the bounding surfaces. In case pressure boundary conditions are specified, it gets a little more complicated. You have to solve both of the equations, the Laplacian of the potential is equal to 0 and the pressure boundary condition with some initial velocity, and then correct that until you get the pressure correct. The relation between the potential, that is, the potential itself is linear in the velocity, because the potential is given by phi is equal to, I am sorry, the velocity is given by ui is equal to partial phi by partial xi, and I am solving the Laplace equation for the potential. Therefore, the velocity is a linear function of the potential. If I increase the velocity by a factor of 2, the potential at all points will also increase by a factor of 2, subject to an unknown constant. Note that since the velocity is related to the derivative of the potential, I could always add a constant value to the potential without changing the velocity field. In other words, I have to specify the potential equal to 0 at some point, then I will have the potential at every point within the fluid in terms of the potential at that particular location, subject to an unknown base value, because the velocity is only related to the gradient of the potential. Velocity is linear in potential. Therefore, if the velocity were to be increased by a factor of 2, the potential gradient goes up by a factor of 2 everywhere within the flow. That means that this term in the Bernoulli equation will also be linear in the potential. However, I have a quadratic term here proportional to u square. So, if I reverse the velocity everywhere, this term does not change sign. Therefore, the pressure is no longer linear in the velocity. Recall that for Stokes flow, the pressure and the fluid velocity were all linear in the velocity of bounding surfaces. In this particular case, the fluid velocity will be linear in the velocity of bounding surfaces. In other words, if I change the velocity by a factor of 2, the fluid velocity at each point will increase by that same factor. The pressure will not, because the pressure is nonlinear. In fact, you can show that the solution for these equations are unique and they satisfy some minimum energy criteria. Okay. So, these are the basic equations for potential flow. In the next lecture, we will look at some of the properties of these equations, then go on to solve some specific problems. Just to reiterate, we have neglected inertial viscous terms in the conservation equation. So, the equations are inviscid. In addition, we have considered irrotational. Therefore, the rate of deformation tensor is symmetric at all points within the flow. In that case, the velocity can be expressed as the gradient of the potential. Potential satisfies Laplace equation. The stress is equal to minus P times delta Ij, because we have neglected viscous terms, and the pressure is related to the velocity and the potential through the Bernoulli equation. We will look in the next lecture at how to solve these equations, and some of their general properties. So, we will see you then.